Imagine a distant world, so remote that it has only been visited by a single spacecraft. And that fleeting encounter happened back in the mid-1980s. Imagine drifting far beyond the orbit of Saturn, past the ice giant Uranus, and into a haunting realm between Uranus and Neptune. A cosmic no-man's land where sunlight is a pale whisper, and temperatures plunge to levels that would freeze air solid. Now, picture astronomers peering through the darkness and suddenly spotting something remarkable. A cosmic companion, a minor planet moving in perfect gravitational synchrony with Uranus, tracing an invisible pattern that has endured for at least 1 million years. What if this discovery could flip our understanding of how the solar system works, and even hint at possibilities for life in the most unexpected places? Welcome to the wild frontier of the solar system's outer reaches, a vast expanse littered with icy fragments, mysterious moons, and secrets that have eluded humanity for millennia. In this video, we will unravel the story of Uranus, one of the solar system's most enigmatic planets, and its newfound partner in cosmic choreography. We will journey through cutting-edge astronomical discoveries, explore what they mean for the future of planetary science, and consider how insights from these distant worlds might even reshape how we build resilient systems on Earth. Let's begin at the heart of the mystery, Uranus itself. Discovered in the late 18th century, Uranus is the seventh planet from the Sun, and it is unlike any other world in our cosmic neighborhood. With an axial tilt of nearly 98 degrees, Uranus does not spin upright like Earth, or even roll gently like Jupiter. Instead, it literally rolls around the Sun on its side, its poles alternately basking in sunlight or shrouded in darkness for decades at a time. This extreme tilt, likely the result of a massive collision or a long-lost gravitational resonance with another planet, has baffled astronomers for generations. Uranus's magnetic field adds another twist to the puzzle. Unlike Earth's, which is roughly aligned with its rotational axis, the magnetic field of Uranus is dramatically tilted and off-center, creating bizarre and unpredictable auroras. The planet's pale blue-green hue, a result of methane in its upper atmosphere, masks a world of complex weather patterns, faint rings, and at least 27 known moons, some of which may hide oceans of liquid water beneath their icy shells. Despite its size, Uranus is more than 4 times wider than Earth and contains over 14 times Earth's mass. It remains the least explored of the giant planets. Only one spacecraft, NASA's Voyager 2, has ever visited Uranus, and that was during a brief flyby in 1986. Voyager 2 revealed much, but left even more questions unanswered, especially about Uranus's strange magnetic field, its enigmatic rings, and its mysterious moons like Ariel, Miranda, and Titania. For decades, the vast expanse between Uranus and Neptune was thought to be a region of chaos and instability, populated by countless small, icy bodies known as centaurs. These odd objects straddle the line between asteroids and comets, boasting orbits that are constantly perturbed by the gravitational pull of the giant planets. Most centaurs have short, tumultuous lifespans, lasting from a few million to tens of millions of years, before being flung inward to become comets, or outward into the frozen abyss. But in recent years, astronomers have made a breakthrough that is forcing a dramatic rethinking of the outer solar system. A team led by Daniel Bamberger from the North Holt Branch Observatories in Germany, along with international collaborators, meticulously combed through years of archival telescope data. Their detective work paid off. They identified a minor planet, designated 2015 OU-194, locked in a precise and stable orbital dance with Uranus. Let's break down what makes this so astonishing. For every 3 trips this centaur makes around the Sun, Uranus completes exactly 4. This is known as a 3-to-4 mean motion resonance, a mathematical relationship that is rare and, in this case, astonishingly stable. Imagine 2 dancers moving across a cosmic ballroom, never colliding, always perfectly in step, their motions guided by the subtle tug of gravity rather than a choreographer's baton. Alessandro Morbidelli, a planetary dynamics expert from the Observatoire de la Côte d'Azur, explains, "Resonances are the invisible architects of planetary systems. They create patterns of stability out of chaos, shaping the destinies of planets and minor bodies alike." What truly sets this discovery apart is the stability and longevity of the resonance between Uranus and 2015 OU-194. Computer simulations suggest that this celestial partnership has endured for at least 1 million years, and may last for another 500,000 years into the future. This is not a fleeting encounter or a temporary alignment. It is a gravitational alliance that has persisted through countless cosmic upheavals, from planetary migrations to the shifting architecture of the Kuiper Belt. Even more intriguing, this is the first time astronomers have found such a stable resonance between Uranus and a minor planet in the region between Uranus and Neptune. While this zone is cluttered with icy debris, it has long been thought to lack the kind of stable, long-term relationships that are common closer to Jupiter or within the asteroid belt. The identification of 2015 OU-194 is like finding a perfectly tuned lock amidst a sea of tumbling keys. But the story does not end with a single object. Bamberger's team uncovered additional candidates, such as 2013 RG-98, which also appears to maintain a similar 3-4 resonance with Uranus for hundreds of thousands of years. A third, 2014 NX-65, shows a strong gravitational influence from Neptune, hinting at a complex web of interactions that scientists are only beginning to unravel. What does all this mean? The main conflict is not just the rarity of the discovery. It's what it suggests about the very foundations of planetary formation and the evolution of our solar system. If minor planets can become locked in stable, million-year-long gravitational partnerships with giants like Uranus, could there be many more such cosmic alliances hidden in the darkness? Are these resonant relationships fundamental to the structure of the outer solar system? Or are we witnessing a rare exception? Daniel Bamberger puts it succinctly: "We have only scratched the surface. Every new centaur found in resonance is another piece of the puzzle, potentially rewriting the history of how our solar system came to be." The stakes are far from academic. Centaurs are not just silent cosmic wanderers. They are dynamic agents of change. Their unstable orbits mean that, over millions of years, they can be pushed inward by the gravity of the giant planets, becoming short-period comets that sweep through the inner solar system. Some of these comets may one day cross Earth's path. Understanding the orbits and behavior of these objects is not just a matter of curiosity. It could play a role in protecting our planet from unexpected visitors. Hal Levison of the Southwest Research Institute points out, "Centaurs are the missing link between the distant Kuiper Belt and the comets that occasionally light up our skies. By studying their orbits and interactions, we gain insight into the forces shaping both the outer and inner solar system." The discovery of 2015 OU-194 also has profound implications for models of planetary evolution. Current theories suggest that centaurs originally formed in the Kuiper Belt, or the scattered disk, far beyond Neptune. Over billions of years, gravitational tugs from the giant planets can scatter these bodies inward, where they may become trapped in resonances, ejected from the solar system, or even collide with planets and moons. Each stable resonance discovered is a clue to the ancient migrations of planets and the chaotic early days of our cosmic neighborhood. Beyond the science, there are practical lessons that ripple all the way back to Earth. The concept of resonance, where different parts of a system move in harmony, reinforcing each other, appears not only in planetary dynamics, but also in economics, technology, and even social systems. Financial markets, for instance, can achieve stability when different actors move in sync, while technological ecosystems thrive when innovations build upon each other in coordinated cycles. The lesson is clear. Hidden patterns of order often emerge from what appears to be chaos, if we look closely enough and analyze the right data. For students, entrepreneurs, and lifelong learners, this is a call to action. The breakthrough that led to the identification of 2015 OU-194 did not come from a brand new telescope or a billion-dollar mission. It came from combining years of archival observations, creative thinking, and tenacious analysis. In a world awash with data, the next big discovery could come from re-examining old records with fresh eyes, using new algorithms, or collaborating across borders and disciplines. As technology continues to advance, the barriers to scientific discovery are falling. Amateur astronomers and citizen scientists now have access to powerful tools, robotic telescopes, global data sharing platforms, sophisticated simulation software that were once the exclusive domain of elite research institutions. The upcoming Large Synoptic Survey Telescope, soon to be operational atop a Chilean mountain, is expected to revolutionize our view of the night sky. Over a 10-year survey, it will scan the entire visible sky every few nights, generating a flood of data and potentially revealing hundreds or even thousands of new centaurs. Some of these may be locked in similar resonant dances with Uranus, Neptune, or even more distant giants. With each new discovery, our understanding of the solar system's architecture grows richer and more nuanced. We are learning that the space beyond Neptune is not a featureless wasteland, but a dynamic, evolving region shaped by subtle gravitational relationships and ancient migrations. Each centaur tells a story of survival, chaos, and order, a story that echoes the grand narrative of the cosmos itself. But what about the future? What lies ahead for the exploration of Uranus, its cosmic partners, and the frigid depths of the outer solar system? The coming decades promise to be a golden age for planetary science. NASA's proposed Uranus Orbiter and Probe mission, tentatively scheduled for launch in the early 2030s, aims to deliver the first detailed investigation of Uranus since Voyager 2's flyby nearly half a century ago. This ambitious mission would carry advanced instruments to analyze Uranus's atmosphere, magnetic field, and ring system, as well as conduct close flybys of its moons. By probing the planet's interior and sampling its upper clouds, scientists hope to solve long-standing mysteries about Uranus's composition, its bizarre tilt, and the origins of its unusual magnetic field. Perhaps most tantalizing is the prospect of exploring Uranus's moons, especially Miranda, Ariel, and Titania. These icy worlds are believed to harbor subsurface oceans, warmed by tidal heating generated as they orbit the giant planet. Unlike the frigid cloud tops of Uranus, these hidden oceans could be kept liquid by the constant flexing and squeezing of the moon's interiors. If confirmed, they would join a growing list of so-called ocean worlds in the solar system, alongside Europa, Enceladus, and possibly Ganymede. NASA scientists and members of the international space community are increasingly fixated on these moons as potential habitats for life. Radar sounders and magnetometers aboard future orbiters could detect the telltale signs of subsurface water, while landers or sample return missions could search for organic molecules and chemical signatures of habitability. With every new mission, the line between planetary science and astrobiology grows thinner. China, too, is entering the race to explore the outer solar system. The Tianwen-4 mission, scheduled for a possible Uranus flyby in the mid-2040s, will add another crucial data point to our understanding of these distant worlds. Together, these missions could spark a renaissance in our understanding of planetary formation, orbital dynamics, and the potential for life beyond Earth. Of course, exploring the outer solar system is not without its challenges. Spacecraft must survive temperatures close to absolute zero, withstand radiation, and maintain reliable communication across billions of kilometers. Innovations in power generation, propulsion, and data transmission will be essential to making these missions a reality. But the potential scientific rewards are vast. New insights into the origins of the solar system, the nature of planetary interiors, and the possibility of life in the most unexpected places. Let's return for a moment to the broader implications of the discovery of 2015 OU-194. Astrophysicist Alessandro Morbidelli reminds us that resonances are not mere mathematical curiosities. They are the fundamental forces that shape planetary systems. Stable resonances, like the one observed between Uranus and its newfound partner, could be the key to understanding how chaos and order coexist in the space beyond Neptune. Imagine entire families of minor planets, dozens, perhaps hundreds, moving together in harmonious patterns, sculpting the architecture of the solar system over billions of years. Yet with every opportunity comes risk. The very forces that create stable resonances can, over time, destabilize orbits and send centaurs careening into the inner solar system. The Centaur 29P Schwarzmann-Wachmann 1, for example, is famous for its frequent outbursts, possibly linked to cryovolcanism, and shows just how unpredictable these objects can be. Another, 2008 kV 42, was the first discovered with a retrograde orbit, demonstrating the astonishing diversity within the centaur population. Carlos de la Fuente Marcos, from the Complutense University of Madrid, notes that co-orbital objects like Crantor provide valuable test cases for understanding the gravitational dynamics near Uranus, even though their stability may be limited over astronomical timescales. Each new discovery challenges our models and forces us to refine our understanding of the delicate balance between chaos and stability at the edge of the solar system. But perhaps the most profound lesson is philosophical. In a universe that often seems indifferent to order, the persistence of stable cosmic partnerships over millions of years is a testament to the hidden structure and beauty of nature. It reminds us that even in the coldest, darkest corners of space, there are patterns waiting to be discovered. Patterns that can inspire new ways of thinking about systems, resilience, and the emergence of life. So what practical insights can we take from all this? For economists and technologists, the concept of resonance, offers a powerful metaphor. Just as planets and minor bodies can form stable alliances through the subtle interplay of gravity, so too can human systems, markets, networks, and organizations achieve resilience through synchronization, feedback, and adaptation. By seeking out the hidden connections and reinforcing loops within complex systems, we can build structures that are both robust and flexible, capable of withstanding shocks and thriving in uncertainty. For educators and students, the story of 2015 OU194 is a call to embrace curiosity, perseverance, and the value of interdisciplinary thinking. The fact that this breakthrough emerged from archival data analysis, rather than expensive new hardware, shows that ingenuity and collaboration are as important as technology in advancing knowledge. As more data becomes available and analytical tools become more sophisticated, the next wave of discoveries may come from unexpected places, and perhaps even from someone watching this video right now. In summary, what have we learned from the stable dance of 2015 OU194 and Uranus? We have glimpsed the intricate negotiations that shape the solar system, seen how order can emerge from chaos, and open new chapters in the search for life and understanding beyond Earth. The outer solar system is no longer a silent, frozen wilderness. It is a frontier teeming with dynamic relationships, hidden oceans, and lessons for both science and society. And here's a secret that few people realize. Although Uranus has only been visited once, its moons may harbor some of the most promising environments for life in the solar system. Beneath the icy crusts of Ariel and Titania, moons larger than many dwarf planets. Tidal heating may keep vast oceans liquid and potentially habitable, even as the surface remains locked in perpetual winter. The search for life, it seems, may one day lead not to Mars or Europa, but to the distant, shimmering moons of Uranus. So what comes next in this grand cosmic adventure? Stay curious, follow the data, embrace the unknown, and remember, sometimes it is a million-year-old partnership hidden in the darkness beyond Neptune that can teach us the most about the universe and about ourselves. If you enjoyed this journey to the edge of the solar system, don't forget to subscribe, share your thoughts in the comments, and join us next time as we uncover more